I'm going to try doing some of the curve fitting stuff in Desmos. That'll give me some new abilities, but it's not a good place to do all the stuff we were doing right here in the previous video. I'm going to copy my kind of X data or time data and Y data, and I've got hundreds of rows of data. I'm just going to use some of it. In your project, you should probably use all the data you have. Come to Desmos here, and I can just hit. First of all, notice that I'm not including the words here, just all the numbers. I'm going to copy that, paste it into Desmos here, and it makes a table. And I can retitle this. I can call it like T1 for my first list of time values. And this Y, I could call it Y. I could call it like lymph to say which compartment we're dealing with. And it graphs it for us, so that's nice. I've already got that set up here. And then I typed in a prediction formula. That's just a surge curve, and I put some parameters on it, and I can graph that, and you can see it's kind of as far off as my first guess was in Excel. And I can play with the parameters here and stuff like that, but I'm still a long way from being where I need to be. We're going to turn that back off, and I'm going to turn off the graph of the data table here. And we're going to do something more interesting. I'm going to say, here's the prediction formula again, but this time instead of letting my parameters be sliders, I'm going to say that they're arguments to the function. There's things you can put into the function, and then the function will use them. And I had to give them different names than the sliders already had, so I gave the sliders names with a subscript. It doesn't matter what subscript it is, but here I'm not using subscripts. And then here's where life gets interesting. We're saying let's take the actual Y values, subtract the prediction you get, so that's computing residuals, and that gives us a list, because the lymph values, that's a list of Y values. T1 is a list of T values, so it'll give us a list. It'll subtract each component of the list pairwise, like first from first, second from second, third from third. Then it will square each of the resulting list values. So because doing actual Y minus predicted Y is the residuals, then it squares each residual. Then it takes the mean of all those, so that's mean squared error, and then takes the square root of it, so that's root mean squared error. And the fun thing here is what I'm letting it adjust is the vertical scale and the power component parameters. And this is only a 2D program, so I can only get two variables, so I had to put in some value for the other one here. Let's actually go check what we were using in Excel. It was 0.35. And then we can ask, what is the RMSE value at any particular spot? So let's use what we're using, 0.1 and 4. And we get 14.76, which is roughly hopefully roughly what we were getting over there. I think the list is a different length, so we won't worry about that. But we want to see what values make this as small as possible. And so that's just giving us one number, and I could play with these to adjust my V and P parameters. But the really cool thing is in Desmos, you can say, here's a function of x and y. Show me where it's equal to 1, where it's equal to 2, where it's equal to 3, 4, 5, all the way up to whatever upper limit you want. So I'm going to, I know I need to zoom in first, because remember we're dealing with parameter values that are like point something or 3 point something. So I'm going to zoom in here. And then I'm going to turn this on so it graphs it, and it takes a while to think about it. Maybe I'll even pause. Okay, I paused it while Desmos was thinking about stuff, and it's giving me contours here. I don't really care about the negative x values. So everything along this curve has the same RMSE value. everything along this curve has the same RMSE value, etc. And I want to get to a curve that indicates the lowest RMSE value. So if I say RMSE of A comma B, and I put a point A comma B, then as I move this around, it's telling me what's the RMSE at that point. And apparently RMSE is getting worse that way, so I want to go this way. So I'm trying to move RMSE to find the minimum possible, move this point to find the minimum possible value there. So being on one of these higher contours gives me a worse RMSE, and I want to move this way. That gradient stuff we did in Excel is actually telling us which way to move for any particular place we're at. So it'd be nice to know a better fit. Like our fit right now was not very good, right? If we look back at what it was in Excel, that's still not a great fit. Desmos has a way of doing the fitting for us that's really interesting. We can say, I want to model the lymph, and instead of an equal sign here, I hit tab just to get out of the subscript. Instead of an equals, I'm going to hit a tilde, which kind of means approximately equals, and then give it a formula that it can use to take the T1 values, that list of values, and raise it to the, I think it'll get upset if I do a P here. I'm going to do a Q because that's like P, times e to the negative r times T1, and it, what didn't it like? Superscripts cannot be empty. Do I have a superscript? I don't know. Oh, there we go. It just took a while to realize what the syntax was. So it's saying the best values of V, R, and Q to use to make this formula get close to these values are these. So it's done that curve fitting for us. It's actually done a fancy version of all that. Find the gradient, take a little step, find another gradient, take another little step. And it even says what the R squared is. If you've seen that in statistics, it's like the new RMSE versus the RMSE for a really dumb model. As the closer it is to 1, the better. And it computes the residuals for us, so we can plot those. We'll see those later, actually. But this tells us where to focus. So instead of 0.35, I'm going to focus us on 0.067, and we know we need to look around x equals 0.001 and power of 3.3. So I'm going to, so that's kind of interesting. So it's saying we can get kind of good results out here. Oh. It's so slow because it's having to recompute these. But you can see all these contours here. Down here, my RMSE is like 13. Up here, the RMSE is like 28. But if I kind of follow the gradient or follow the opposite of the gradient to minimize my RMSE, then I'm getting RMSE values of like 0.6, sorry, 6 point something, 5 point something. So if I start zooming in here, then I'm getting RMSE values that are even better. It's just taking a while. So that gradient is telling us take steps this way or that way based on where you are to kind of go downhill as quickly as possible till you find kind of the bottom of the valley. And you can see I've got an even better RMSE here. So somewhere around there. So that's kind of what's going on behind the scenes when Desmos is doing this curve fitting. it's computing gradients and going in the opposite direction to make the RMSE lower and everything like that. All right.